Hi, so welcome to Math 150, Section 1, 2021, probably Lecture 8. So that's usable, excellent. And so what we're going to do today is talk a little bit about partial differentiation. I am going to try the class math today to see if that does a better job for the people at home who are listening. For those of you who would like to sponsor a multivariable calculus lecture, I will waive corporate sponsorship for the stuff. So what I want to do today is talk about how you would actually calculate, partial derivatives in practice and what the theory is behind doing the calculations in full rigor. And then that's not going to take a tremendous amount of time, so we'll have time to review a bunch of topics as well. And again, from the computational perspective, once you prove certain theorems, you get to use them. You don't have to go back to the drawing board. You don't have to go back and do the theoretical derivation all over again. Has anybody ever taken the derivative of this function before? Okay. What's the derivative? (1701x) 1700. So you did not need to go back to the definition of the derivative. F of x is the limit as h goes to 0, f of x plus h minus f of x over h. And then put in what f of x is, expand. Once we prove that formula, we can just use it. Whenever you have a formula, you always want to check and make sure are the conditions satisfied. So you might remember the geometric series, the sum goes from 0 to infinity of x to the n, 1 plus x, x squared, x cubed, is 1 over 1 minus x if the absolute value of x is strictly less than 1. We don't have to redivide this every time we want to use it. When we want to differentiate functions, functions of several variables, we have rules that we can use to find the derivative. But we have to make sure that the function is differentiable. So I think I mentioned in the video that there are some bad functions like x, y to 1/3. What do I mean by that? Is this function continuous? Yeah. Are there any points of x and y where you worry about the continuity of this function? So the two things I need to worry about is, am I dividing by 0? Am I ever dividing by 0? No. Am I taking the square root of a negative number? No. I'm taking the cube root. What's the cube root of 8? 2. Now there are other cube roots of 8. Not negative 2. The other cube roots involve complex numbers. All the cube roots of 2 will have absolute value 2. There are 2 other roots too. And in fact, if I give you, as an aside, x cubed minus 2 equals 0, well, x cubed minus 8 equals 0, we know that x equals 2 is a root. That means x cubed minus 8 must be divisible by x minus 2. You might remember, you may have repressed the memories, polynomial division from algebra. Do you know the method of divine inspiration? The way the method of divine inspiration works is you just write down the answer. And so I feel divinely inspired, and let me guess that it's x squared plus 4x plus 4. And if I multiply things out, I'll get x cubed. Maybe I made a mistake here. So if I multiply it out, I'll get x cubed plus a 2x squared minus a 2x squared, so they cancel. Then I'll have a 4x minus a 4x, so they cancel. And I'll have a minus 8. So this is actually the factorization for the difference of 2 cubes. I know the root of this. When does x minus 3 equal 0? X equals 2. Can we find when x equals 2x plus 4 equals 0? Yeah, quadratic formula. So we can actually find the roots of x cubed minus 8 equals 0 without too much trouble. if we know how to factor the difference of two fields. But even if you don't know that, I can only give you this formula you can see in this special case. It's not so bad. What's nice about this is it's clear. If I have things that are cubed, I don't have to worry about square roots of negative numbers. What if I want to find x cubed plus 8 equals 0? So I want the cube root of negative 8. What would the cube root of negative 8 be? Negative 2. And again, we could play the same game, and there's going to be two other roots, 2x cubed equals negative 8. But there's still going to be a nice one. So when I give you xy to the 1/3, the places that you should be concerned about, this was a section earlier in the semester, is when is the function defined? Stay away from zeros in the denominator. Stay away from square roots of negative numbers. So in both of those cases, everything is fine. If I take x to be 0, what is f of 0y going to be for any y? It's just going to be 0. And by symmetry, if I take y to be 0, 0. So we have a function that is 0 along the x-axis, it's 0 along the y-axis. So if I want to calculate the partial of f with respect to x, and I evaluate it at any point where x equals 0, what will that be? So I'm calculating the partial derivative. So if you want, I like to have functions tell stories. If I go back to this case, f of x is x to the 17/1. Think of that as your distance. So if f gives you distance, what's the derivative of f going to give you? Speed. I want you to calculate my speed. At all moments in time, I'm 0 units from home. How fast am I moving? 0. I am not going to make the traffic. Right? My speed is 0. So if I tell you the function is always 0, when we go back and go into the definition and you change by a little bit, do we still expect to get 0? Let's see. So let's calculate. So we would look at the limit as h goes to 0, f of 0 plus h comma y minus f of 0 comma y over h. And let's see that's always going to be 0. So what happens if I put in 0 plus h? I will get that this is equal to the limit as h goes to 0. 0 plus hy, I'm going to get hy to the 1/3. What is f of 0y? Zero. And I divide by h. H is very, very small. Which is larger, h or h to the 1/3? H to the 1/3. If you look at this, this is the limit as h goes to 0 of y to the 1/3, h to the negative 2/3. If you think of h as 1/8, the cube root of 1/8 is 1/2. You have a 1/8 down below, so it's going to be 1/4. So when we look at this, what's going to happen as h goes to 0? It diverges. Okay, so I thought that maybe this is 0 is a little bit off. It wasn't a bad guess, but it turns out it's not zero. When we try to calculate like this, what are we doing? We are fixing x to be 0. We're going up to a little bit of value of y over here, and we're approaching like that. Right? X is 0, y, and then, then we move x over a little bit. We're coming in like this. So the function is always 0 along the line. But as you get very, very close, what's happening to the function? What does xy to the 1/3 look like? So for fixed value of y, as x gets very, very small, what does xy to the 1/3 look like? Is it going to 0 or is it going to infinity? I'm sorry? So you have x times y to the 1/3. So the fixed value of y, as x gets smaller and smaller and smaller, think of x as h, it's a small number. Is h to the 1/3 going to infinity or is it going to 0? Not infinity, it's going to 0. So imagine h is 1 over 1,000. What is h to the 1/3 going to be? 1/10. Imagine h is 1 over 1,000 to the 6th. Then h to the 1/3 would be 1 over 1,000 with, I would have 1/3 of this. 1/3 of it. H to the 1/3 is still going to go to 0. Is it going to go to 0 as rapidly as h? No. But it's going to go to 0. So it's sometimes nice to just put in some specific values and just play with it. And so when we do this, we see that our function f of x, y is still going to go to 0 as we approach the y-axis. Well, that's good. We want that if the function is going to be continuous. And we know it's 0 along the axis. So as we approach the axis, we should get 0. But the rate of approach is interesting. When we go through and we try to calculate the derivative, and we look at f of hy minus f of 0y, and we go through and we do the calculation, we see that it diverges. Let's try looking at df dx at some point x comma 0. So now we're going to stay on the x-axis. Before, we were on the y-axis. And so this will be the limit as h goes to 0 of f of x plus h0 minus f of x0 over h. What is f of x plus h comma 0? xy is xy to the 1/3. So if I put in x plus h for x and I put in 0 for y, what do I get? 0. And I get 0 here as well. So the numerator is always 0. So the limit is 0. And the difference here is I'm doing df dx. So here, I choose some point on the x-axis, and I approach my point in one of the two ways. But since my function is always 0 along the x-axis, if your distance is always 0, what is your speed? If your distance is always 5, what's your speed? If your distance is always 23, your speed is 0. So if your distance is constant, your speed is going to be 0. And because our function is not changing on the x-axis, if I do df dx on the x-axis, that's going to exist. Instead of doing df dx on the y-axis, which should I look at? So I did df dx on the x-axis, and that exists. What should I have done on the y-axis that probably would exist? Differentiating with respect to y, because then I would be moving up, down. And if I'm moving up, down on the y-axis, I start at some point and I move a little bit. And on the y-axis, the function is identically zero. What I was doing here is I was calculating partial f, partial x. And so I'm moving a little bit left. And so this gives you an example of a function where df dx and df dy exist at the point 0, 0. But I can't just take the derivatives everywhere. And so this example tells us we have to be a little bit more careful. If you think about it, if you just did things formally, df dx should be d by dx of x to the 1/3, y to the 1/3. Let's stay away from points that are 0. So I have this as my function. What would you get when you take the partial with respect to x? What rule would you use to evaluate this? Would you use the product rule? So a product of two functions. What rule should I use? I could use the product rule, but there's an easier rule to use to take this derivative. You treat y as a constant, so what rule should I use? The constant rule. This is just going to be y to the 1/3 d by dx of x to the 1/3. And so this would just be, the derivative with respect to x would just be 1/3 x to the negative 2/3. So we would have y to the 1. And that would be partial f, partial x. And this gives us some idea of why there's going to be a problem. Is this function always well defined? Is this function continuous, or does this function have issues? Issues. So where does it have its issue? Yeah, with x equals 0. So not continuous. Issue if x equals 0. So the moral of the story is if your partial derivatives are continuous, then the function is differentiable. So here, df dx and df dy exist and are continuous, then f is differentiable. So we're not going to prove that theorem. I hope the theorem seems reasonable. And that you can see that, if the partial derivatives are not continuous, one of them doesn't exist, that should be a pretty good warning that something is going on. Now, if we try to calculate the derivative at the origin, everything is going to be fine at the origin for this function. Because as we come along in standard paths, the function is identically 0 along the x-axis, it's identically 0 along the y-axis. So the question is, what is the right generalization of differential? And so we have this definition from before, and we talked a little bit in an earlier class about how there's many ways of writing what it means for a function to be differentiable. This is the standard. Sometimes instead of having x, we have the point x naught. Is it a big deal to put an x of 0 here? And then sometimes instead of saying h goes to 0, we instead have x goes to x naught. Well, that's not a big deal. That's basically just saying let x equal x naught plus h. So we want to try to maybe generalize. And we saw a really good way of writing this is f prime, is the limit as x goes to x naught of f of x minus f of x naught minus f prime of x naught and x minus x naught over x minus x naught equals 0. And this seemed like a good way. We just subtracted off the f prime from both sides. We multiplied by 1 so that everything had a common denominator. And we're saying take your value, subtract off where you stop, subtract off your instantaneous speed at that point times the elapsed time. And it should be such a good approximation that even when you divide by the elapsed time, it goes to 0. So one idea is, well, why don't we just generalize this to a function of several variables? So imagine x is now a vector. What would x minus x naught be if x and x naught a vector? What kind of quantity would that be? It would be a vector. But this is the value of a function. That's a real number. I can't divide a real number by a vector. Hey, not a big deal. Put an absolute value. And how would we generalize the absolute value? So instead of taking the absolute value of a number, we would take the length of the vector. So we could look at the limit as x goes to x naught, and then down below would be the length of x minus x naught. And then we would have f of x. Think of that as maybe f of x, y, z, f of x1, x2, x3, whatever. I forgot input. Subtract off where we start, and then subtract off df 1 at the point x naught. I'm going to use the letter A here. That'll be a little bit. So x1 minus a1 minus dfn xn minus an. So what we're doing is we're taking our partial derivatives, evaluating them at the point that matters, and then multiplying by how much we're moving in that direction. So we only had one thing, we just reduced to what we had before. There's a lot of different ways to view this. So we need some notation. And so we use big D of f as A. We sometimes write, I think it's normally called upside down triangle. It's interesting as to which is considered upside down and which is considered regular. Sometimes we write grad. We would read this as grad of f at the point A. And this will just be df dx1 at the point A, df dxn at the point A. So it's a vector. Do you see any dot products of them? Yeah. So what we have is we have the limit as x goes to A of f of x minus f of A minus the gradient of f A dotted with x minus A divided by the length of x minus A. Do I need to put an absolute value in the numerator? Well, the numerator is a number. So if the whole thing is going to 0, I don't need the absolute value. You can put the absolute value if you want. This is what it means for a function to be differential. This is the generalization of the standard notion of derivatives. And the old notion of f prime of x times x minus x naught is generalized to the gradient of f at A at the point dotted with x minus x. And what this is essentially saying is the tangent plane or the tangent hyperplane does a terrific job of approximating. This is the generalization. Think of the gradient of f as your normal direction. And here's how I get my plane, normal direction dotted with where we're going. So think of this as the normal direction. All right, so this is the definition of what it means to be differential. After you see the definitions in Calc 1, do you ever go back to them to compute a derivative? No. You just use the rules of differentiation. And that's exactly what we do in multivariable calculus. We just go and we use the rules of differentiation. We never go back to this. We never want to compute this. This is a nightmare. This is the theory that allows you to do. And the reason I started with things like the geometric series is to just remind you, when you want to use a theory, you have to make sure the conditions are satisfied. If the conditions aren't satisfied, it means nothing. You can't apply it. And so here, if this limit goes to 0, then the function is differential. How do you compute this limit goes to 0? Well, we can take the partial derivatives, because that's just the Calc 1 problem. These partial derivatives are, we specialize, the coordinate axes are nice. These are the ones that really matter. We calculate them the same way we normally would. We take the dot product, and then we do some algebra, and we show that this goes to 0. More generally, what you do is you just prove that this works for a large factor function. If f is a product of, if f is a polynomial in the variable, it's a product of, say, x's and y's and z's, then the limit is going to. If f is trigonometric, it's just sines and cosines, it's going to. If it's exponential, it's going to. Combinations of things that exist in this. If you then start taking ratios, if f is, say, polynomials divided by polynomials, what do you have to worry about? Going to 0. Or if you start taking things to, say, fractional power, do I have now maybe a negative number to a square root? Or if I have something like x, y to the 1/3, my danger is now when I take the derivative, I could actually have something coming in the denominator and going up. All right, so now the question was, how do we actually compute? So to compute things, you just do what you would have done in Calc 1. You just want to be careful about notation. I am one of the managing editors of the Journal of Number Theory, and we got a paper that was claiming to prove one of the biggest open problems in mathematics. And I told the author, I don't think you have it. This paper, I think, has serious issues with how it's written. The author kept introducing new notation every few lines, where this would actually be the same as this would be the same as this would be slightly different than this. And I said that this is not a good approach. And as I figured, the author confused himself as to what was going on, and his error was an error of notation. He was applying something like the geometric series in a place where it should not have been applied. You want good notation. If I give you a function, the f of x, y, z is x squared y z cubed, don't write things like d by dx equals. And so what would be the partial with respect to x? Square. Because I can just use y z cubed as a constant. Why can't I just write d by dx equals f. What am I taking the derivative of? Right? D by dx is an operator. It has to operate on something. I can't just have d by dx floating. What do I apply it to? In this problem, I'm probably applying it to f. So it's wrong to say d by dx equals d by dx applied to f. If I really wanted to be pedantic, I should say what point this is being evaluated. Normally, with abuse of notation, we just say, if I don't write anything, it's just a point x, y, z. We saw a moment ago, however, it can get a little bit confusing when I have x minus x naught and what's going on, how am I writing things. So it's sometimes not a bad idea to just put things in. Right. This is similar in Calc 2. You have to go from 0 to 1 of f of x dx. We know that this means send x from 0 to 1. How many of you were ever in a class where they would write x equals 0 to 1? No one is raising their hand. And the reason is because in Calc 1, when you have something like this, there's only one variable in play. Right? The only thing that's variable is x. It's clear that it's x that's running from 0 to 1. But when we have several variables, it's no longer so clear. And now it's actually useful to write x equals 0 to 1 if we have more than one integration going on. So if we want to take derivatives, we can now just go exactly as before. All right, so before I do anything else, any questions on what we've done till now? Any questions on other things from the section? Did this answer your question? Yes. What yes, it's giving us yes, and we will talk about that in a lot greater detail later. That the gradient of f is a vector, and so the question is, what direction is it pointing in? And we'll talk about how you can actually use that to try to find where a function is largest or small, to find maximum and minimal through optimization. And this is extremely important in economics for doing the branch multiplier. Anybody here who is thinking of doing economics, this is something that will come into play. Okay. What if I give you a of x, y is f of x, y, g of x, y? What do you think I want to discover now? Giving you a function a is the product of the function f and the function g. What do you think I'm going to be looking for? The derivative. So what rule am I going for? Right. Shouldn't there be a multi-dimensional product rule? Maybe I'm getting ahead of myself. Is that the first thing we should look for? Product rule? Or should we start with something a little bit easier? What would be an easier thing to start? The sum. So let's put a plus sign over here and make this the sum. So what do you think the derivative of the sum would be? The sum of the derivative. So the derivative of the sum is the sum of the derivative. The derivative of the difference is the difference of the derivative. The derivative of a constant multiple is that constant multiple times the derivative. And it comes back to, if you go back to the definition, because they're a sum, you can just split them into each function independently. And the proof is essentially the same as the one-dimensional sum. And so you would get the a dx is equal to the f dx plus g dx, or partial f partial x plus partial g partial x. More generally, you could say the derivative of a, or like that, the gradient of a, or the grad of a, any of these is fine, is equal to the gradient of f plus the gradient of G. And if you wanted to write this in vector form, it would be df dx plus the G dx df dy plus dg dy. It's important to remember when I have the gradient of the triangle of the capital D, it's a vector. When I have things like this, it's just individual numbers. These are the components going into the vector. It is not a bad idea whenever you're doing problems like this to just pause and ask yourself, what beast am I studying? If I'm studying a vector, I should have more than one component. Okay. So the other rules are pretty straightforward. Difference is the same, constant multiple is the same. The product gets a little bit more interesting. So let's say I have a of xy equals f of xy g of xy. Could I have more components? Could I have to just do 2 components? Could I do 3 components or 5 components? Yes. Is it going to be that much harder? The only thing that's going to change is there'll be more notation on the board. And so I might have to do maybe x1 dot 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 x that. So rather than doing that, let's just focus on just 2 variables, because 2 variables will highlight what's going on. So you can always add them up. One of the biggest principles in mathematics is to be lazy. It is actually a good thing to be lazy. How can you be lazy? You try to reduce whatever you're given to something you already know how to do. How many of you have already completed a course in multivariable calculus? Which is to be expected given that this is a multivariable calculus. How many of you have completed a class in one variable calculus? Okay, so you know how to do one variable calculus. So the goal is whenever I give you something in several variables, can you reduce it somehow to something in one variable that you already know? So we know that the derivative of A is just dA dx, dA dy. Oh, okay. We just have to figure out what the different partials are. Okay, that's not so bad. So d by dx of A would be d by dx of f of x comma y g of x comma y. But I'm viewing f and g, or the functions of 2 variables. Y is fixed. If you want, view this as a new function, script f sub y of x, script g sub y of x you want. Your y is fixed. How would you take the derivative of a product? It would just be what rule? Product rule. So what's the derivative of fg? It would be f times g plus fg prime. Except now we have to be careful. What do we mean by f prime? What would f prime be here? We're taking d by dx with f of xy, g of xy. So instead of an f prime, what would we have? So in order to be able to calculus, when you have f of x, g of x, the prime means derivative with respect to x. That's the only variable in play when we have f of x, g of x. We're considering y fixed. We're taking the partial derivative with respect to x. So if I just had functions of one variable, I want to say f prime g plus fg prime. But I can't write f prime. Because when I write f prime, I don't know what I'm taking the derivative with respect to. What am I taking the derivative with respect to? with respect to x. So instead of writing f prime, what should I write? Yeah, so this would just be partial x times g of xy plus f of xy partial g partial x. So if I plug this in here, I get the derivative of a. The first piece is going to become df dx times g plus f dg dx. What's the second piece going to be? So the second piece is I take the partial with respect to y rather than the partial with respect to x. So all that changes is instead of having partial f partial x, I now have partial f partial y. So it'd just be df dy times g plus f times partial g partial y. And now we need to do algebra. So the goal is, can we write this in a more illuminating manner? df dx times g, df dy times g. F dg dx, f dg dy. I can write this as a sum of two vectors. Let's have one vector involve just derivatives with respect to x, derivatives of f, and one vector involves just derivatives of g. So I can write this as df dx g plus df dy g. And the second vector would be f dg dx f dg dx. So you can see if you add them together, df dx g plus f dg dx. Oh, good. That's exactly what this piece was. I put this part in here, and I put this part in here. For the second one, df dy g, I put that here, and f dg dy, I put that here. I've just taken my expression, and I've written it as the sum of two vectors. This is actually a really good thing to do. Do you notice anything in common in the first vector, the two components? Anything in common with those two components? The g, I can pull this out and df dx df dy times g. And the second one, what's common? What do we have in both of them? Yeah, which we can pull out an f. It'll be dg dx, dg dy. Should I be worried about which side I pull out f to? No, it's f a vector. No, f is just a number. So this is actually the gradient of f times g plus f times the gradient of g. What we want is df times g plus f times dg. Doesn't this look a lot like the product rule? The derivative of a product in one variable was f times g plus g prime. G of fg is the derivative of f times g plus f times the derivative of g. It's the same. The only thing that changes is now I don't have a prime. I have to remember that this is a gradient, that this is a derivative, that this is a vector. I did this in the case of a function with two variables. It is an entirely analogous argument to do this if you have more than two variables. Right? If I had three variables, the proof would just be a little bit longer. If you want, as a good exercise, to try to prove this in general, to show that it continues, that it generalizes. Do you think that there's going to be a similar rule for the quotient rule? No. So we have to worry, because what do you have in the quotient rule that you don't like? I'm sorry? Not the cube, the square in the denominator. So do we have to worry when we generalize that we want to have a vector squared down below? We have to worry about it. We're going to be okay because it's the value of the function squared. It doesn't involve any derivatives. The derivatives in the quotient rule are only upstairs. And so if you go through and you do a very similar argument, if A instead was f of x divided by g of x, divided by g of x here, it would just be the standard quotient rule over here, and you would get a very similar result at the end of the day. One way to calculate things is to always go back to basics. Look, if I give you two functions f and g, I can multiply them out, and then I'll just take the partial derivative directly. The reason we don't necessarily want to do that is this rule makes things simpler. So I call him the patron saint of mathematics for the wonderful advice he gave. The advice is simplify, simplify. So the cultural extra credit, who said simplify, simplify. Develop. And of course, if he was truly going to simplify, how would you simplify the phrase simplify, simplify? Simplify. But I guess the extra simplify is for emphasis. Before you do any calculation, you always want to ask yourself, is this the right thing to compute? Is this the right way to compute it? I could multiply things out, but the idea is if I can break things up into smaller parts, those might be easier calculations. One of my favorite problems is the Farmer Brown problem. He has cows, and the cows have to live in rectangular pens. And if you're given a certain amount of fencing, what is the maximum area? How many of you have done this problem? How many of you know the book Tick Tock Move? How's the type? Farmer Brown has a problem all day long. If you were to do this, you eventually get to a function f of x equals x times 1 minus x. How would we take the derivative of x times 1 minus x? What rule would we use? Good. You don't use the product rule. You expand it. This is the same as x minus x squared. I would much rather take the derivative of that directly than to use the product rule and have the derivative of x times 1 minus x plus x times the derivative of 1 minus x. It's much better just expand. So whenever you do these calculations, always take a moment and think, what is the best way to do? All right, so this is a good place to stop.